Hello again and welcome. My wife's brother found this meter in a house that they were getting ready to demolition. This is made by a company called TMK. You can see the case is in pretty good shape. It's all made out of leather. There's a strap that holds the meter into the case. I believe these may actually be the original leads, but I'm not so sure about these alligator clips being the original. These are both marked Mueller Electric Company, Cleveland, Ohio, USA series. But the wire looks to be the period, and these are soldered in place, so I suspect that these are actually what was supplied with the meter originally. You can see the wire almost looks like it's extruded. It's definitely not smooth like a modern silicone wire. You can see there's a small crack in the lens right here, but other than that, the meter is in very good condition. It also came with the original paperwork. This is the test report. You can see serial number 3511093. If this shows up on the camera, just above my thumb, this is marked the same serial number, 3511093. So this is actually the test report for this particular meter. You can see the room temperature was 23 degrees Celsius. It was 58% humidity. Its inspection date was January 26th of 1974. We have the name of the two inspectors. And here's the calibration report for it. We can see on the top the appearance looked good, no cracks I'm assuming. The zero adjustment worked fine. No sticking, no friction. I have not seen a meter like this that came with the original paperwork. So I know that this particular meter was built in 1974. So I have here some trade magazines. This is CQ, QST in 73. This one's dated 1975. This is dated 1973. And the CQ magazine is dated 1970. So I was looking for advertisements for TMK. In this copy of CQ, in the very back, there's an ad from a company called Herbert W. Gordon Company in Massachusetts, helping hams to help themselves. And if you look very carefully, the dial for this meter appears to be identical to the dial that's on our meter. So I'm not 100% sure, but I wouldn't be surprised if this particular meter was not produced by TMK. He calls this the model M500, and I don't know how well this will show up on the camera, but just below here, at the very bottom of the screen, we see a model M-500. The very nice thing about this meter, you can see it has the mirror for lining up the meter. Of course, our meter doesn't have that, so this is a little fancier. But this particular meter is actually a vacuum tube voltmeter. What I found interesting about this ad is it says hams require the 5,000 volt DC range. In competition, even at substantial increases in price, do not give this range. Exquisitely crafted with a superb switch and idiot-proof design. And that's actually what it says right here. It's an idiot-proof design. That's what we need today, idiot-proof designs. But this is the only ad that I found in any of my trade magazines that looked even close to the TMK. Online, I found some other ones. There was an ad for one on eBay. This one here shows, again, it's a Model 200C. But notice that it actually has jacks here on the right, where ours has a fuse holder. This is an older serial number. See, it starts with the letter R, and then it has 5 digits. that starts with a 2. Ours is a 7-digit number, starting off with a 3. So I suspect that this meter is actually the predecessor to this meter. And I did find this ad online. This is the TMK 200. And if you look, see, it has the 3 jacks on the side, just like this meter does. As a matter of fact, these two meters look identical. So I believe that the original meters made for IBM under the Model 200C were actually this TMK 200. And for some reason, they decided to add this fuse. I'm not even sure why IBM had this meter produced. Maybe their own technicians were using it or something, and they had field problems where the meters were getting damaged or something, and maybe they decided to add that fuse later on. So I did come across this schematic. This is a TMK model TP-5SN. And this schematic is actually fairly close. This schematic for the TMK, this doesn't even come close to matching this meter. What I did is I took this schematic as a starting point, and then I reverse engineered this meter, and I marked up the schematic, and that's what we have here. So this now matches the meter I have. But as I was going through the meter, I realized what had happened is they put the fuse right between the battery terminal minus here and the common point. So this is there to protect you if you were to hook this up to, say, your AC line power, and that basically goes through the battery through this 20.5 ohm resistor right back to the common point. So they never even thought about protecting this shunt. So what I was thinking is, what if we modified the meter to put the fuse not only between this plate but over to the current plate, and then basically you would still have your AC and DC volt ranges without the fuse, so those would continue to work, but at least when you're in the 500 milliamp range with this 0.8 ohm shunt, you would protect that shunt resistor as well as the wiring of the meter with that same fuse. So this meter has actually been modified that way. You know, and with this thing having very little value, I don't think that that's a problem. Even though the one ad talks about it being idiot proof, at least for that model, we know this one isn't. So if I did do something stupid, at least that fuse is going to protect the meter itself from me. Let me just show you what's inside of this meter. You can see there's 3 small screws on the back cover. See, there's 2 small rubber standoff posts. These are what are holding the batteries in place. So let me show you some of the repairs I did with this meter. I didn't have the actual parts that broke out of this, so I built this entire corner up using epoxy resin. And then I took a Dremel tool and I reshaped this edge into it. And then I sanded this all back to the shape of the case. And I just took a magic marker and I went over the epoxy. That was the only crack in the lower section of the case. You would think that this has the original batteries in it. It's pretty close. So these are kind of a trick battery. I wanted to preserve the ones that came with this. And so I made these battery covers. This is actually turned down aluminum. And there's a small spring down inside of here. So they had this plastic sleeve over the outside of the battery, and then they crimped this metal band over it. So I took a razor blade and I cut this band off. You can see the joint right here. And then I carefully slit the side of the jacket, and I took all this apart. And then I resoldered the seam back together, and I epoxied the sleeve back onto the cell. You can see it basically looks like the original cell. See, these are made in Japan by the Fuji Electrochemical Company, Tokyo, Japan. This is their Novell series. Top run black, 100% seal. I'm guessing this battery is probably a little over 40 years old and it never leaked. Neither one of them did. So that's pretty impressive that they could make a battery back then that would be just standard alkaline, and of course it sat in the meter for all those years and it never leaked out. So that's pretty impressive. So what about if these little batteries leak? Of course, these are some pretty cheap ones I've got in here. These were supplied with one of the other meters. So my long-term plan is to replace these with some nickel metal hydrides. I've yet to have a nickel metal hydride battery that's leaked. So why not just install the new battery? Well, as it turns out, these batteries are about 1 millimeter shorter than what a modern AA is. So with this thing being spring-loaded now, I can insert this into these no problem. Well, when I was looking, this had the original fuse in it, and the fuse hadn't been blown, which I thought was kind of strange. The reason I think it's the original fuse is this is marked KSG, and I've never heard of that company before. When I looked it up online, it does appear to be a Japanese company. So this meter was found in the United States. If they had ever blown the fuse, I wouldn't think that they would go out and try to find a Japanese fuse to replace it. So you can see, and now I have a fast blow. This is from little ceramic fuse. This is still not a safety fuse, but that's rated for 500 milliamps, which should be plenty fast enough to save this shunt. So what I'm going to do is save this original fuse. But this way, if I want to play around with the meter at all, if I screw something up, at least I'm not going to damage that original fuse. Alright, so I suppose you're probably wondering if the meter actually works. Let's just give a little demonstration. So we're going to start in the resistance mode. So this will give you a pretty good view of the scales. At the bottom you can see this is the 15 volt AC scale. The next one above is the resistance. So you can see to the far right, this would be 0 ohms, and on the far left, this would be infinity. So currently the leads are open. If I short these together, and then I can adjust the little thumb wheel, it's sitting here, we use that to zero out the meter, and we'll put this right at 0 ohms. And now what I'm going to do is attach a 50 ohm resistor. So on the 1x scale, 50 ohms would be right here. That looks pretty good. That's right on the 50 mark. So let's just try that with a 100 ohm resistor. And again, we're right on the 100 mark. What I can do now is go up one scale, and let's re-short the leads. And you can see the meter's off a little bit. So we'd have to bring this back down to the 0 point. Let's just try it on the other modes. So this is 100 times, and this is 1,000 times. So it looks like those three modes pretty much match. It's really the 1x mode that's off just a slight amount versus the other three. Alright, so in the times 10 mode, let's go ahead and apply a 100 ohm resistor. And you can see it's right on the 10 mark. So 10 times 10 would give you your 100 ohms. So what I'm going to do now is go up one scale, and I'm going to apply a 1000 ohm resistor. And again, it's right on the 10 spot. And let's go to the 1000x mode, and I'm going to apply a 10k ohm resistor. And again, you can see we are smack on the 10 mark. So let's just try going up a little higher. This is with a 100k ohm, and you can see it's now on the 100 mark. Let's just try it with a 1 mega ohm. A little difficult to tell at this point. I think really this is probably about the limit of it at 100k. I think you start getting much higher than that, this meter isn't going to do a whole lot for you. But I assume that the people that they were selling these to probably didn't have a need for that high of a resistance measurement. Alright, so currently I have the Bryman meter on the right The 2 meters are attached in parallel, and I'm going to connect them to my power supply. And you can see I have the IBM meters set for the 1.5 volt DC scale. May be difficult to tell, but you can see it's right at 0.6 volts. Basically dead on with the Bryman. And you can see, so we're at the 5 volt scale now. And I'm applying roughly 2.5 volts. And the meter is basically dead center. Again, it looks quite accurate. You can see we're now on the 15 volt scale. And we're right at the 9 volt mark. And that corresponds with what the Bryman's reading. Let's go up to the 50 volt scale. Alright, you can see our Bryman is currently displaying roughly 25 volts. So the top one is at 5, and then it's 50, and then 500. So 25 volt would be mid-scale. We can go up to the 150 volt scale. Alright, you can see we're putting out roughly 50 volts. The 150 volt scale is just above my thumb. This is 60 volts. And over here is 30. So there would be 40. And 50 volts right there. So again, the meter is spot on. I don't have a big power supply out here. We can go to the 500 volt scale though, and we'll just leave this with the 50 volts applied. And again, we can see there's our 500 volt scale. So here's 100 volts. So 50 volts would be halfway between the 100 and the 0 volt mark. And again, it looks pretty close. Alright, so you can see I have the 2 meters tied in series right now, and the Bryman is set to the milliamp range. You can see we are supplying roughly 250 milliamps. So again, you can see our IBM is set for the 500 milliamp range, which is this scale right here. So down here, this would be 200 milliamps, and that would be 220, 240, 260, 280, 300. So it looks like it's displaying just about 240 milliamps, which is fairly close to what the Bryman is displaying. So one thing I should mention here again, I had rewired this meter. So if I take out this fuse, right there. So if we were to supply too much current, it would actually take out this fuse now and hopefully save that shunt. And of course, let's just put this into resistance mode. And if I again short the 2 leads together and I remove the fuse, you can see that works just fine. The IBM is set for the 50 milliamp range, and we can see the 50 milliamp range right here. So 25 milliamps would be halfway down the scale. So it's a little off, it looks like, maybe just slightly low. Again, it kind of depends on the angle. Alright, so I've changed it to the 5 milliamp scale. And you can see we're putting out roughly 5 milliamps on the Bryman. And you can see that's basically full deflection. Again, this would be our 5 milliamps at the very top here. You can see we're now on the 500 microamp scale. And you can see we are putting out just about 300 microamps, which is pretty much what the Bryman is showing on the right. So it seems like all the current modes on the IBM meter work just fine. Alright, so I have the 2 meters tied in parallel again, and you can see I'm putting out roughly 10 volts right now at 50 hertz. So on our IBM, you can see it's set for the 15 volt range. So you can see there's the 15 volt range. So here's 9 volts, and here would be 12 volts. So there's 9, 10, 11, 12. So it looks like about 9.5 volts. So it looks like it's reading slightly lower than what the Bryman is reading. Still not too bad. Alright, so you can see We're set on the 50 volt range, which is going to be this one here. So this would be 40 volts, and down here would be 30. So again, it looks like it's reading just a little bit on the low side. You know, and I don't have any paperwork that says how accurate these are supposed to be. Let's just try it at the 150 volt scale. So here's our 150. So there would be 90, 60. So there's our 30 mark right there. And again, you can see it's reading just slightly low. I don't have any way to generate anything close to 500 volt AC right now. You can see it does go up slightly. So it looks like probably all the AC ranges are just a little low on this meter. The only thing I'd like to show you is that, again, if I were to remove the fuse, you know, that has no effect on the AC or the DC mode. Alright, so both meters are currently again in parallel, and you can see we're putting out roughly 5 volts at 50 hertz. Again, this is a sine wave, and the IBM meter is set for the 15 volt scale. That's the most sensitive scale it has. So our 15 volts is over here. This would be 6 volts here and 3 volts here. So again, it looks like our meter is pretty much dead on at 5 volts right now. What I'm going to do is increase the frequency a little bit, and let's see how that affects this meter. So let's start by going down in frequency. See, we're all the way at 4 hertz right now. Here's 100, 200, oh, it's just starting to move. So that's pretty impressive. You can see we're at 13.2 kilohertz right now, and we have just hit the 3 dB point. So the 3 dB point would be 5 times 0.707, or roughly 3.5 volts, and that's roughly where we are right now. So it's a pretty good AC response for the analog meter. And again, I have our 2 meters tied in parallel, and I'm putting out a sine wave again that's going between 0 and 5 volts peak. Currently I have the IBM meter set for the 5 volt range, and I have our Bryman set for manual ranging, and you can see our bar graph on the bottom of the Bryman. So let's see how fast this Bryman can keep up compared to our analog meter. We're just going to slowly start increasing the frequency. Okay, so you can see our Bryman meter is still basically using the full scale on this bar graph. You can see how much it's attenuated on our IBM meter. So currently, this is at 1.04 hertz. So this is at 2 hertz. And again, we can see the Bryman is still reaching full scale. That's one thing about this Bryman, is the bar graph on this works pretty good. So I sent an email over to the IBM archives basically asking for history of this meter, you know, why it was that IBM had it built, if it was just used for internal use or whatnot. It'll be interesting to see if they write me back. But if you have any information about these old meters, I'd be interested in hearing from you. Just post what information you have down in the comments. I think other people would appreciate that as well. Well, I think that's going to be it for the video. I appreciate all you new followers. Glad to have you on board. And until the next meter, later.